So we're super excited to have James today. He's going to be talking to us about, first of all, he's a student at Berkeley with Sanjam, and he's going to be talking to us about post-quantum multi-party computation. So we're very excited. Take it away, James.
Okay, thanks. So yeah, I'll be discussing this upcoming work on post-quantum MPC. This is joint with Amit, Vipul, Dakshita, and Julio. And so yeah, sorry it's not online yet before the talk, but it will be in a few days. So, okay. So yeah, so first I'll go through an outline of this talk. So I'll start with an introduction, like motivate the question, and discuss some challenges that are specific to the post-quantum setting. And then I'll basically have three technical sections. So the first, I'll discuss a parallel no-cloning simulation technique that we develop in this work. And this is built off a recent technique that has been introduced in these three works. And I'll be reviewing this technique and then showing how we extend it to the multi-party setting. And a technical tool we use to do that is quantum multi-key FHE, which we construct. And so in this section, I'll discuss Mahadev single key quantum FHE, and then how we build on that to get the multi-key variant. And finally, another technical tool we need are post-quantum non-malleable commitments. And so I'll discuss these in the final section. Okay. So first, yeah, so what is secure MPC? We have a set of parties. They each have their private input, and their goal is to compute some public function, some circuit over all of their private inputs. And they'll do this by communicating with each other. And for security, we want to say that if we have an adversary that is corrupting and controlling some set of parties, we want to say that this adversary doesn't learn anything about the honest party inputs through interacting in this protocol, except for what it should learn from just the result of the circuit. Okay, and this is really a general, widely studied notion in cryptography with many flavors of security definitions, and most of these flavors are based on what type of adversary we're considering. And so one very common setting is to say, let's consider computationally bounded adversaries. So we'll restrict them to run in polynomial time, but we'll allow them some arbitrary number of corruptions. So they can corrupt, say, up to n-1 parties, as long as they choose who to corrupt before the protocol begins, and then proceed from there. And we'll let them act, once the protocol starts, we'll let them act in an arbitrary, malicious fashion, meaning they can instruct the parties they corrupt to compute their messages in an arbitrary way based on any polynomial time strategy. So this is a very familiar setting, and indeed, this is an incomplete list of citations of works that have studied exactly this setting of MPC. With a computationally bounded adversary, computationally bounded malicious adversary. So everything I've discussed so far, I've been in the classical world. I guess all these machines are classical machines. They have classical inputs, and they want to compute a classical function. So we're going to stick with that. But we want to ask what happens when we give the adversary more power. So namely, we let the adversary actually be a quantum polynomial time machine. And studying in cryptography in the last couple of decades, studying classical primitives secure against quantum adversaries has been a huge research direction, especially in encryption, digital signatures, and so on. But in the MPC setting, it turns out once we go to this setting, not much is actually known. So there's these works in the two-party setting that give basically a way to do general two-party computation, secure against quantum adversaries in a polynomial number of rounds. And as far as we're aware, in the multi-party setting, there's, there hasn't been any works that have explicitly studied this. This is where our main result comes in. So, what we show in this work is there exists a classical MPC protocol that is actually just constant rounds in the plane model. So this was implicit in the slide. In the last slide, I wasn't assuming any sort of trusted setup. So we have this classical MPC protocol in the plane model secure against quantum polynomial time adversaries. And so we're going to need to assume so the mildly superpolynomial hardness of learning with errors, along with the polynomial hardness of some circular security assumption. So I'll say a little bit more about these assumptions before moving on. So that the first, what do I mean by mild superpolynomial hardness? It's just that no quantum polynomial time adversary has advantage better than 1 over lambda to the iterated log of lambda in breaking LWE. So this is very barely superpolynomial. In particular, this is like weaker than assuming, say, the quasi-polynomial hardness of LWE. And this assumption we need in particular to build our post-quantum non-malleable commitments. So the circular security assumption is what we use it to do is to build quantum multi-key FHE. And in fact, a special case, we end up needing a special case of multi-key FHE, which I'll explain later, but it's going to be spooky encryption, which is a classical notion, but we port it to the quantum setting, and it's just basically, it turns out to be a special case of multi-key FHE. And what we use this to build is first of all, a constant round parallel extractable commitment. And the novelty here is in the parallel setting, and just so you have like a picture in your head, a parallel extractable commitment is a setting where you have a single receiver interacting with multiple committers at once. And you want to say if there's an adversary that corrupts all of these committers at once, then even in such a case, there exists an extractor that can extract all of their inputs. And so even if these like committers are operating in parallel. So we also use this quantum multi-key FHE to build parallel zero knowledge. It's a similar setting where we have multiple verifiers interacting with one prover. If they're all corrupted at the same time, there's still going to be a simulator that simulates their view. Okay, so these tools, this parallel zero knowledge, this parallel extractable commitment, these non-malleable commitments, they all we combine all of these to end up with our constant round MPC protocol.
James, there's always like this subtlety when we deal with post-quantum stuff, which is like who's quantum and who's not, and like particularly for interactive primitives, right? So like I guess even in MPC, there's like a question of like I'm some classical like honest party, can the adversary run me in superposition, right? I guess the answer is usually no to that, yeah. But now I'm very confused about quantum multi-key FHE because that sounds like there are quantum circuits involved. So like we really are gonna, like the good guys are gonna run a quantum computer as well.
So we'll get to this, but honest parties are going to be completely classical, and the running the quantum circuit only comes up in the security proof. When we want to simulate the adversary's view, right? Adversary is going to be a quantum machine, so.
I see. Sounds very cool.
James, a couple more questions.
Yeah.
So this circular security has nothing to do with sort of leveled versus fully homomorphic encryption. You're using it for completely different purposes. Is that right?
Leveled versus, I mean.
So usually circular security sort of gets you from leveled homomorphic encryption to really fully homomorphic encryption.
Yeah, I mean
right?
that's essentially what we're using it to do in this setting as well.
Oh, that is okay. Okay, I see. Interesting. Yeah. And I guess the second question is: is the MPC protocol you get? It's constant round, but is it also succinct?
Is it also succinct?
Because you use
so it actually depends on. I guess maybe what. So as you'll see, we're going to use basically a post-quantum MPC protocol in the CRS model, which already exists. So if that's succinct, then I believe that our protocol should be succinct.
So your building block is a post-quantum MPC in the CRS model with many rounds, presumably, right?
Yeah.
Okay. All right, thanks.
Yeah.
So one more question is that do you make black box use of the adversary or make non-black box use of the adversary?
Non-black box. Yeah. So yeah, I mean, we'll see all of these shortly. Okay. So yeah, so as I just said, basically this approach is to take these post-quantum MPC protocols with trusted setup exist in the literature, and these are some examples of them as long as you instantiate them with appropriate like post-quantum primitives. So yeah, for example, like this Mooger JWix, for example, is going to be succinct. So even better. So yeah, they have trusted setup, but the trusted setup is nice in the sense that it's just a common random string. So it's as unstructured as possible. And how the security proofs in these protocols work is the simulator first programs a CRS with some trapdoor, and then it simulates a completely straight line from there. And so this works well with quantum adversaries. So for us, it suffices to basically have the parties first agree on a common random string, a CRS, and then run one of these protocols with respect to that CRS. And so this basically amounts to showing how to build a coin flipping protocol in constant rounds. And so I'll get to exactly what I mean by fully simulatable, and you'll see why this interfaces nicely with the simulator strategy of programming the CRS. Okay. So what is coin flipping?
Is straight line a technical term, or do you just mean like at eye level?
It's okay. I guess it is. I guess it's become a technical term. It just means that basically the simulator is not rewinding the adversary. It just kind of yeah.
Makes sense. Okay, thank you.
So yeah, and in fact, maybe I should mention not only is the simulator straight line, it's also black box in those protocols as well. Okay. Okay, so what is this coin flipping functionality? It's a special case of MPC, but it's inputless. So like each of these parties just have no input, and what they want to do is communicate with each other. And at the end of the communication, they want to they want the transcript of their communication to fix some string R. And ideally, this R is going to be some unbiased random string that they can then use as a CRS. So, what's a natural way to try to achieve this? Well, you could have every party like pick their own random string, broadcast it, and then set like the sum of all these strings to be R. So this doesn't work right away because a malicious party could wait to see the honest party's random strings and then choose its own string based on what it sees in order to bias the outcome. So to fix this, a natural approach is to first, have every party draw their string, but then first commit to it and broadcast that commitment. And only after everyone's committed to their string, then everyone reveals what string they committed to. And of course, then they have to prove that, what they committed to actually matched what they broadcasted. And we'll actually want these parties to do this in zero knowledge, rather than just having them do an opening. Because eventually we'll have to simulate the honest parties doing this. So this is why we need zero knowledge here. And then finally, if like all the proofs verify, then the common output will just be the sum of all these strings. Okay. So this is like a template to follow at least. So now I'll say like, what do we actually want, or what do I mean by fully simulatable? What security definition are we going for? Here we have an adversary corrupting some subset of parties. So this adversary is going to control these parties, interact with the honest parties, and in this like real world interaction, this is going to generate some distribution over the adversary's final state at the end of this interaction, as well as the string that was fixed by the transcript. So we want to say that for any such adversary, there exists a simulator where the simulator actually gets as input up here some external random string r star. Okay, so it gets as input some string that's drawn at random, and then after that, it simulates this interaction with the adversary to produce some final adversarial state and a final transcript. And we want to say that the simulator is restricted to outputting a transcript which fixes the string r star that it received as input. And we want to say that these two distributions are indistinguishable. So in other words, like basically the simulator is forcing the outcome of this transcript to be r star. And we want this to be, even though it's forcing this, we want this to be indistinguishable from the real world interaction. So now, maybe you can see like why this is useful. Like if this r star is actually some programmed CRS for one of these CRS model protocols, then the simulator can still simulate this interaction in an indistinguishable way. So I'll discuss basically why this is, some challenges that come up in the post-quantum setting. Recall our general template. We have every party commit, and then broadcast, and then prove consistency. So, like I said, we want to somehow have a simulator force an outcome r star. So a natural way for the simulator to do that is to first interact with the adversary and somehow extract from the adversary's first messages, extract their inputs Ri. And if the simulator can extract what they committed to, then the simulator can set the honest party inputs appropriately in order to fix this outcome r star, right? So this is what we're going to want to do. And of course, a simulator of course, honest parties shouldn't be able to extract from the adversary's commitments because these commitments should be hiding, but the simulator should. So, what is the simulator's advantage over the honest parties? As in any simulation paradigm setting, there's, the one advantage it has is it actually knows the adversary's state. And in fact, can choose the adversary's state. Like this, by state, I mean like maybe the random coins used by the adversary at the beginning, and then like any intermediate computational state that comes up during the interaction. So, okay, so now that the simulator has access to the state, what can it do with it? And so I'm still kind of discussing just the classical setting here. And there's been some really successful techniques that have been developed based around like what can a simulator actually do with an adversary state. And one like hugely successful paradigm is to have the simulator rewind the adversary. And this is something you can do if you have the state. You can always just take the computation back up and redo it, and as many times as you want. Another thing you can do if you don't want to rewind, you can also clone the adversary if you know its state. And so, for example, Barak's technique is doing this. On the one hand, the simulator is running the adversary's next message. Now, on the other hand, it's using a copy of that adversary's state to using as a witness to some succinct argument. Okay. So, in this work, we're interested in quantum adversaries, right? So this adversary is going to be a description of a quantum polynomial size circuit, but its state is going to be, in general, a quantum state. So we're asking, what can a simulator do knowing a quantum state? And it turns out that these two, rewinding and cloning, are problematic. So if an adversary measures its state, then in general, this is not a reversible operation. So rewinding becomes difficult, as first pointed out by Van de Graaff. Although I will mention that there are works that show that you can actually do rewinding in certain settings with a careful argument. Okay, but it's certainly not as widely applicable of a strategy as in the classical case. And then cloning the adversary seems difficult. I mean, in general, cloning quantum states is impossible. So this doesn't seem like a useful strategy. So in this work, we'll be interested in simulation strategies that do neither of these things. Okay. And that'll bring us to the first technical section. So here, I will be discussing what's been called the homomorphic trapdoor paradigm. And this is basically an extraction technique that does not rewind and does not clone. And it's showed up in these works of Bitansky, Khurana, Anand Flafaka, and Bitansky Shmueli in the last year. And so basically, I'll describe how it works. It basically consists of, it makes use of two tools. Okay, the first tool is fully homomorphic encryption. And in fact, the intuition that homomorphically evaluating an adversary's code could be potentially useful in extraction kind of goes all the way back to the BBB impossibility of Barak et al. And it was made more explicit in the Bitansky-Paneth like simulation technique based on unobfuscatable functions. But what gives FHE homomorphic encryption its ability to be used in a non-rewinding way is really its use in conjunction with compute and compare obfuscation. Okay. So here is a it's an obfuscator. What this is an obfuscator for programs of the following form: compute and compare programs that are parameterized by three things: a function, a lock value, and a message. Okay, so on input x, it evaluates f on x, and if this equals the lock value, it outputs m, and otherwise it just outputs nothing. So it computes and compares to the lock value. So these works gave a way to obfuscate these functions, where the obfuscation of a particular compute and compare program is indistinguishable from some simulated program, which you can think of as an all reject program, as long as the lock value has sufficient entropy given the description of the function. And they show how to do this under the LWE assumption. Okay. So given these tools, I can describe basically at this point, I'll be able to describe like the core of the technique. So I'll be setting this up as an interaction between a committer and a receiver, but I just want to stress that this is like what I'm presenting is not a full commitment. It doesn't right away satisfy all the hiding and binding properties we might want. But this is kind of what this interaction is at the core of of the commitments and zero knowledge that these works built. So, okay. So what the committer is going to do is first sample some FHE keys. And it's also going to sample a uniformly random trapdoor value and a uniformly random lock value. Okay. It's going to compute an encryption of the trapdoor. And then it's going to compute the following obfuscation. So of this particular compute and compare program. So what is this doing? It's taking as input a string, which is it's interpreting as a ciphertext. It's decrypting that ciphertext with the secret key, and if that ciphertext happened to be an encryption of the lock value, then it will output both the secret key and the message that the committer is committing to. Otherwise, it will output nothing. Okay. So, given these three things, the committer will release this this message, which is the public key, the encryption of the trapdoor, and the obfuscated compute and compare program. Given this, the receiver will attempt to guess the value of the trapdoor. So it's going to send back some guess for the value of the trapdoor. And the committer will take as input that guess. It'll see, okay, was the receiver right? Did it guess trapdoor right? If so, it'll return the lock value. Otherwise, it will return nothing. Okay, so this is some subroutine in a commitment, but we'll see basically how this allows extraction. Okay.
So James,
yeah.
The trapdoor is just a string at this point. It doesn't seem to have semantics, right?
Yeah, no, trapdoor is just going to be a random string.
Okay.
Yes. Mm-hmm. Yeah, no special structure there. Mm-hmm. Okay, so first, like, why is this plausibly, just to get some intuition, I mean, why is this plausibly a hiding? Like, why is this not releasing the message M to the receiver? Well, first note that, okay, given if FHE is secure, then the receiver like won't be able to guess the value of Trapdoor just given this encryption. Thus the response will just be bot. So lock will be hidden from its view, and if lock is independent of the receiver's view, then you can apply compute and compare security, obfuscation security, to show that this is useless to the receiver. Okay, and thus the message M is hidden. So now I'll discuss extraction using this, but first I just want to let's make the following simplifying assumption. And so let's say that this adversarial committer is explainable. And what I mean by explainable is the following. So every message it outputs is actually going to be in the support of some honest committer algorithm, which means it's consistent with some random coins used by an honest committer. Okay, so it's this notion of explainability is a little similar to the notion of semi-malicious, if you're familiar with that. But the difference is that, or one difference is that this committer is not actually giving the extractor the random coins it used. It's just guaranteed that like the messages it outputs are consistent with some random coins that maybe the extractor doesn't know. And in fact, these random coins could be maliciously generated, right, in any way. So I will say that this is a non-trivial class of adversaries, but also, once you, as these other works kind of followed a similar two-step process, is like once you show that you can extract from such committers, then you can kind of use other techniques to extend extraction from explainable committers to arbitrary committers. And I won't be discussing that in this talk because the main ideas still come in when you're just dealing with explainable committers. Okay. So how does this extraction procedure work? This is, so the extractor now we're assuming it knows the state of the committer, right? And I guess for the rest of this part, you can kind of think of this committer as being classical or quantum. Kind of everything I say applies to both settings. It just depends whether you think of the state as a classical string or a quantum state. Okay, so the extractor now will first run the committer, run these first three steps until it outputs its message and updates its state. So at this point, right, intuitively, in order to extract the message, the extractor is going to need to somehow make use of this compute and compare obfuscation. And in order to do that, it's going to somehow have to come up with an encryption of the lock value, right? And in order to do that, like, it seems like it needs the trapdoor. Like, that's the only way it can extract the lock out of the committer. But the thing is that, it doesn't have the trapdoor in the clear, but it has non-trivial information about the trapdoor, namely the FHE encryption of it. So what it's going to do is run the final part of the committer under the hood of the FHE. In other words, it's going to like take this block of code that is going to be run by the committer along with the state of the committer and evaluate this homomorphically over the encryption of the trapdoor, which it has. And this should output exactly an encryption of the lock value, right? Since this trapdoor is the right value, along with an encryption of the updated state. Okay. So once the extractor has an encryption of the lock, it can directly evaluate the compute and compare program on this lock to obtain the secret key in the message, can output the message, and then finally it can use the secret key to decrypt the final state and also output the final state. So note that this extraction procedure was entirely straight line. It did no rewinding and it did no cloning. So I do want to mention that, again, like I was saying before, this is not a full commitment. One thing that needs to be fixed in particular is this, this step 4. This code actually has to be run under a secure, something called a secure function evaluation, or some like a special case of 2PC. And the reason is we don't want the committer to realize if it's interacting with the extractor or the honest party. And there's a couple other changes that need to be made, which I won't discuss. But hopefully this gives kind of the core idea of how this straight line extraction is working.
Sorry, James, where does the encryption of the state come from?
so this piece of code, it operates like this final commitment, or this final function along, and it operates on the current state of the committer, whatever it is. And so that outputs like whatever the final the value of this function along with the value of the state. The committer, whenever it runs some procedure, it's also updating its internal state as it's doing that, right? So this, if you run this thing under the hood of FHE, what you'll get is the output as well as the updated state. So, and I will note that now, like I said, you can either think of the state as being classical or quantum. In the case that the state is quantum, we will need this FHE to support evaluation of quantum circuits. Okay.
So, okay, sorry. This is kind of trippy for me. So just to be clear, like the function that you're running eval on is the next message function of the potentially adversarial committer. Yes. After message number 3. So the message that gets sent, I see. Okay. Which, like, if the committer were honest, would have this form, but it's not necessarily honest, so it could have some crazy form.
Exactly. Okay. Cool. So this is a paradigm, like this core idea has shown up in slightly different ways in these different papers. BKP to do this, it was actually purely in the classical setting to get some new results in the classical setting, and then these works show the usefulness of this this core extraction procedure in the quantum setting, and they use these to build various things, extraction procedures, zero knowledge. So indeed, yeah. So these two works showed how to basically get new results in constant round post-quantum zero knowledge, and this improved upon these older results, at least in terms of round complexity. So, but note that and like what I just described, and zero knowledge in general is just an interaction between one prover and one verifier. Okay, and so we're asking, is this extraction technique actually useful to the multi-party setting, and in particular to multi-party coin flipping? So that the thing here is that, like, if you think back to the template that I had earlier, what a simulator must do, like an adversary could be corrupting some set of parties that are running these commitments in parallel, and so the simulator must somehow extract from an adversary that is corrupting multiple committers. So we're asking, our challenge here is to basically extend this technique to the parallel setting. Okay. So to be more explicit, let's just, for the rest of this part, let's just consider an adversary that corrupts exactly 2 parties, or exactly 2 committers. So what's going to happen is when you run this adversary on an initial state, it'll first run the first part of these committers, right, and basically output 2 sets of messages, 1 per committer. Okay, the first is going to be the public key, the encryption, as well as the compute and compare obfuscation. The other is going to be exactly the same thing, but generated with independent randomness, right? So at this point, the second part of each of these commitments are going to be these functions that turn the trapdoor into the lock, as we just saw. But the challenge here is that the extractor only gets kind of like one chance to run this final piece of code, and since an adversary in general is just kind of like one machine, you can't basically split these 2 parts up. You can't like run it once and rewind. You can't clone the adversary. So this is really just one function that has to be run a single time, and intuitively we're going to be wanting to run that homomorphically over both an encryption of the trapdoor 1 and an encryption of the trapdoor 2. Okay, and these are encrypted under different public keys, potentially independently generated public keys. So here's what we want to do. We want to evaluate this code over these 2 encryptions. But so how do we evaluate something over 2 independently generated public keys? It turns out we have a tool for this, which is called multi-key FHE. So here, if you take an encryption under 2 independently encryptions under two independently generated public keys, you can take a circuit and evaluate it over them, and out comes the response, so C of M1, M2, encrypted under both public keys at once. So when you run this evaluation procedure, what you'll end up with is indeed encryptions of lock 1 and lock 2 under both public keys at once, along with an encryption of the updated state. Okay, so does this mean we're done? Like, can we run the same final procedure as we saw in the single committer case? So let's look at it a little more carefully. So what does the extractor have at this point? It has encryptions of lock 1 and lock 2 under both public keys. And then it has a compute and compare obfuscation with one of the secret keys hard-coded and a compute and compare obfuscation with the other secret key hard-coded. So now note that it's not immediate that you can basically evaluate either of these compute and compare programs on either of these encryptions because these ciphertexts are just simply not in the right form. And and even worse, like this ciphertext, like you kind of need both secret keys to decrypt it. So one thing you could try to maybe do is have the set of committers like tell them to like somehow jointly sample a compute and compare program that has both of the secret keys hard-coded in it, but this appears to require some sort of general purpose NPC, which is what we were trying to build in the first place. So we'll basically show how to make do with just this information. So everything, I'm just doing this in the two committer setting, but everything I explained can be generalized to an arbitrary number of committers, and in particular when this encryption is under like a set of n public keys at once rather than just two. Okay, so the first step, and I'll describe later how to do this, but the first step is to convert these multi-key ciphertexts into nested ciphertexts, right? So now we have an encryption under public key 1 of an encryption under public key 2 of the lock value. And you can maybe see already why this is useful. Now, under the hood of take the second encryption, under the hood of public key 1, you actually have something that is functions as a useful input to, say, the second compute and compare obfuscation. Okay, so we're going to evaluate the compute and compare obfuscation homomorphically under this public key 1. Okay, so we'll take this guy, evaluate the compute and compare obfuscation. So what's happening here? That you evaluate this compute and compare obfuscation on an encryption of lock 2. So that's going to be successful and output, in particular, the secret key 2. So what you end up with is an encryption under secret key 2 of secret key 2 under public key 1. Now, you can use this guy, like combine it with this first encryption here, right? So you have now under public key 1, you have an encryption under public key 2 of the lock, as well as the secret key 2. So you can simply decrypt under the hood to get an encryption of lock 1 under public key 1. And now this can be directly plugged into this first compute and compare obfuscation to recover the secret and message in the clear. So now basically, yeah, let's pause for a second. Basically this, once you uncover like one secret key, you can kind of recurse and like basically recover everything. And also note that this procedure can be also recursed as long as like, if you have an encryption under like PK1 through PKN and you have like n different compute and compare obfuscations, you can kind of like recursively do this two-step procedure and like basically peel off one public key at a time and eventually recover all the secrets. Okay.
So one question is that for the case of many parties, wouldn't the size of these nested ciphertext grow?
So yeah, they don't actually grow because each time, like basically in each time you peel a layer off, you evaluate the compute and compare obfuscation, and then you use that to decrypt, and then you basically update all of the encryptions by like basically peeling off one of the public key layers. So I guess you can see it as like basically in doing this nested conversion, maybe you're kind of adding a layer, but then you're like peeling it off with this compute and compare and decryption. So you never have to actually blow up the ciphertext. Okay. Right. So now it remains to show basically how to do this conversion into nested ciphertexts. So this is what it remains to show. And to do this, we basically use a special case of multi-key FHE. And that is going to be something referred to as additive function sharing spooky encryption due to Dotis et al. And what this is this encryption, what it allows you to do is take two encryptions under independently drawn public keys, evaluate a circuit on them, and what you get is still two encryptions under independently generated public keys, but where the XOR of the plaintext is actually equal to the value of the function. Okay. And this can be seen as a special case of multi-key FHE, where ciphertexts have this particular property, like this particular structure. You know, an encryption of X is actually two encryptions, one of Z1 and one of Z2, where Z1 and Z2 XOR to X. So if you have an encryption in this form, then you can convert to a double ciphertext as follows. Now you start with you do everything kind of homomorphically under PK1. So you start with Z1, and kind of what you're going to do is homomorphically under PK1, you're going to homomorphically XOR Z1 into Z2, homomorphically under PK2. Okay, so this is kind of annoying to look at, but what's going on is you're running this homomorphic evaluation under PK2, under PK1. And what you end up with is exactly this nested ciphertext. Basically doing, you know, once you XOR Z1 into Z2, then you get an encryption of X under PK2. And again, this is, you know, this generalizes to the multi-party case. Okay. So this is kind of, you know, the techniques that were needed to extend kind of this core extraction idea to the multi-party setting. So with that, I can conclude this part. So recall that, you know, in the end, we actually wanted to be evaluating these adversaries when they were quantum circuits, right? And when in particular their state is a quantum state. So basically, using the techniques I just showed, like, you know, if we're given a quantum multi-key FHE scheme, where first we need classical encryptions of classical messages, and we need this because honest parties are classical. And we also needed this special ciphertext structure. So we show, you know, we extended this trapdoor, this homomorphic trapdoor paradigm to enable extraction from multiple parallel quantum committers. And so, you know, that's like the basic technique, but then, you know, we actually have to build useful cryptographic primitives out of that. And, you know, in the paper, we show how to use this technique, combine it, you know, with various other techniques from the literature, basically to end up with constant round parallel multi-committer extractable commitments, as well as constant round multi-verifier zero knowledge. And both of these protocols are in turn used as building blocks in our coin flipping protocol. Okay, so that, unless there's questions, I can move on to the next part, which will discuss multi-key FHE. Good, okay. So now, yeah, so we needed quantum multi-key FHE. And so I'll discuss basically how we get it. And so first I'll give some basically history about quantum FHE. So these original works, these two works basically, they gave single key FHE schemes for evaluating quantum circuits, but where even if you wanted to encrypt a classical message, you're required to be quantum. And I think they also they only supported bounded evaluation. And note that in our setting, it's crucial for classical messages to be encrypted by classical machines, and we also need unbounded evaluation because in general, our adversaries could be arbitrary size polynomial circuits, or arbitrary polynomial size circuits. And so Goyal also, he gave a multi-key scheme but also with the same drawbacks of quantum encryption and bounded evaluation. So, finally, Mahadev, followed by Berkersky, they both gave single key FHE schemes that kind of satisfy everything we need, but in the single key setting, which is unbounded evaluation and this classical encryption property. So our approach is to start with Mahadev's scheme and extend it to the multi-key setting. So now all of the schemes that I cited on the last slide, they all follow the same paradigm called the key encapsulation paradigm, and this makes use of the quantum one-time pad. And so what is this thing? You can take an arbitrary quantum state. You can draw a classical bit string. So let's say K is some random classical bits, and you can use those classical bits to perfectly encrypt this quantum state. So it's just analogous to the classical one-time pad. So this is basically a perfect encryption of the state phi, and you can do this with only classical information. So now, a quantum fully homomorphic encryption in all of these schemes of a state phi consists of two parts. You use a classical FHE scheme to encrypt the key to a quantum one-time pad, and you give that out along with the perfectly mixed state with respect to the key K. So this is what a QFHE ciphertext looks like. So now, how do you do evaluation? I mean, I'm going to be extremely high level and kind of not get into any quantum details, but basically, for a certain set of quantum gates, which are called Clifford gates, they allow the following very nice evaluation procedure. So take your ciphertext, which consists of two parts. You can directly apply the gate to the quantum part, and you arrive at the updated state phi prime, but potentially encrypted under a different key K prime. Now, completely in parallel, you can run the FHE evaluation of some circuit that depends on the gate and update the key from K to K prime. And so this final ciphertext will be a valid encryption of phi prime. Okay. So this just works for these Clifford gates. But the problem is, Clifford gates are not universal for quantum computation, so you're going to need to support some non-Clifford gate, and this is basically where all these schemes on the last slide differ in how they handle this. And so Mahadev gave a way to evaluate some particular non-Clifford gate using parallel operations, but also using something called an encrypted C0, where again, I won't get into the details about how it works. I will just show basically a flowchart of one particular step. This is basically the only step that that requires like this non-parallel evaluation. And so this is how it works, or not really how it works, but how it looks. So you have an encryption of a bit B, which is like, say, one of the bits of your key. So first, what she did is she converted this encryption into an alternate encryption scheme. And she needed this encryption scheme to support some special properties that in general aren't supported by FHE schemes. Okay. And then she used, an encryption in this special form can actually be used to come up with some quantum circuit that evaluates this transformation. Okay. Uses in some sense, it's actually like teleporting the bit B into the superposition. In doing this, a byproduct of this evaluation is a measurement. And what that measurement is actually another AHE encryption of some other bit B prime. And I'm writing explicitly here the randomness that was used to generate this encryption. So you actually, in doing this transformation, you measure a ciphertext. And then, as a final step, you actually have to convert this ciphertext back into an FHE encryption. But not only do you have to convert the bit B prime, you also have to uncover an encryption of the randomness used in this encryption scheme. So this basically requires a trapdoor for AHE, basically something that allows you to recover the randomness used to generate any given ciphertext. And basically the reason for this is that the randomness that was used to generate the ciphertext is now somehow embedded in this key K prime. So of course you need to like recover an encryption of this to maintain this invariant. Okay. So this is a very high level, and I'll go a little bit more into like how she actually set up these encryption schemes. So what was used was for FHE was a dual version of the GSW fully homomorphic encryption scheme. And for AHE, it turns out that the basic dual regev scheme actually satisfies the properties necessary to carry out this operation here. An FHE scheme doesn't satisfy the properties, but it turns out the dual regev does. And so this is actually particularly nice for the following reason. So let's look at what a dual GSW encryption of a bit B would be. So you have a public matrix A. AS plus E, and then you basically add the bit B times a gadget matrix. This is just what dual GSW looks like. Now note that if you just take the final column of this ciphertext, this is exactly a dual regev encryption of B. Okay, that's just what it is. So this means that if this FHE public key is drawn along with the trapdoor tau, then that trapdoor automatically also functions as a trapdoor for the dual regev scheme, okay, because it's a trapdoor for A. So therefore, like if you just draw this FHE public key with a trapdoor, you can then use that trapdoor in this conversion, and so you're done. Okay. So good. So our challenge now is to basically what we want to do is we want to replace the single key classical FHE in this scheme with a multi-key classical FHE, hopefully in order to derive like a quantum multi-key FHE. Okay, so remember that the single key FHE that was used was a dual GSW with a trapdoor. So we're asking the question: does there exist a multi-key FHE scheme where even like multi-key ciphertexts come along with a trapdoor? Okay, so there's various classical multi-key FHE schemes in the literature, and so they pretty much all have to support a procedure of the following form. It's called expand. So here you have an encryption of a bit B under some public key PKI, and you also have a bunch of independently generated public keys PK1 through PKN, and you want to somehow run a procedure that converts this encryption into an encryption of the bit under all the public keys at once. Okay, so this is you somehow need to support this key expansion procedure. Now, what we're wondering then is, okay, say that each of these public keys is drawn along with a trapdoor. Is there an analogous trapdoor expansion procedure that, like, given the description of these trapdoors, produces a trapdoor that functions as a trapdoor for this expanded ciphertext? Okay, so this is what we're wondering, that does there exist such a thing? And it actually turns, it's certainly not immediate, and it's seems a little difficult to come up with such a thing because, well, for one reason is, in GSW and dual GSW, the ciphertext always maintained the following nice form, like something like AS plus E. Now, in all of these works, the expanded ciphertexts are, highly structured, but in a very different way. And in particular, they lose this form, and they don't really have a nice structure, and it's unclear how to combine trapdoors for each of the individual A matrices to obtain a trapdoor for this expanded ciphertext. So what we do instead, okay, is we basically note that in all of these schemes, expanded ciphertexts do satisfy the following property, and that property is nearly linear decryption. Okay, so given any ciphertext, you can publicly compute a linear function based on that ciphertext, such that if you take the inner product of this vector with the concatenated set of secret keys, then you basically uncover the bit B, masked by, or with just a little bit of noise. So decryption is just evaluate a linear function and then round. and then maybe divide by q/2. So we're basically just going to take advantage of the fact that these multi-key FHE ciphertexts support such a simple decryption procedure, which has been taken advantage of in many other works. But so what we're going to do is, even though our MFHE ciphertext, even though this may not have a trapdoor, what we're going to do is key switch into a scheme where multi-key ciphertexts do have a trapdoor. And so key switching is basically just bootstrapping, but going from one scheme to another scheme. So, homomorphic. So what we can do is homomorphically under this alternate scheme, which I haven't described yet, MLHE, we can homomorphically run the decryption circuit of MFHE, right? And the key is that because this decryption circuit is pretty much just a linear function, things work out such that this MLHE scheme only has to support linear homomorphism, okay? And because of that, we can actually define an easy trapdoor expansion procedure for this MLHE scheme. So in particular, if each of these public keys is drawn along with the trapdoor, then the expanded ciphertext actually just has as its trapdoor a concatenation of all the trapdoors. So basically, on the next slide, we'll see a little bit more clearly how this is why this works. But essentially, the point is that we just took advantage of the fact that MFHE has linear decryption to first convert this ciphertext into a scheme that only needs to support a limited class of homomorphism, okay, in order to define this trapdoor expansion. So finally, I can basically describe some simplified version of the final quantum multi-key FHE keygen, which starts by running the keygen of some classical multi-key FHE scheme. And now what you want to do is encrypt this secret key, right, under the MLHE scheme. And so the MLHE scheme we use is basically just going to be a natural extension of dual regev, okay? So to compute this encryption, we're just basically going to compute a dual regev encryption of SK1. And to do that, we'll generate a public matrix along with the trapdoor. We'll encrypt this. This is just a standard dual regev encryption that supports linear homomorphism. That's why this power of 2 is here. And so basically then, yeah, so this D1 is the ciphertext, and then you can output the public key, which consists of this public key along with an encryption of the secret key. So let's say another guy comes along and does the same thing independently. Our goal is to then, during multi-key FHE evaluation, at some point we'll come across a multi-key FHE encryption of the bit B under 2 public keys. And while this may not have a trapdoor, what we want to do is convert it into an MLHE ciphertext that indeed does have a trapdoor. And we want that trapdoor to just consist of tau 1 and tau 2. So we'll just do this with linear homomorphism. So first, compute the appropriate linear function based on the ciphertext. We have to bit decompose it just to support linear homomorphism. And then usually what you would do if you want is if you want to compute this linear function over these 2 secret keys, you would just take the 2 ciphertexts and compute these products and then add them up. So in our setting, D1 and D2 are encrypted under different public keys. So instead, we'll kind of do this staggered thing. And if you basically work out what this is you end up with an encryption of the bit B under this ciphertext, which looks exactly like a dual regev ciphertext, except that its public key has basically this block diagonal structure. And because of that, so this is what we're calling our MLHE ciphertext. And because of that, you can use this trapdoor tau 1 to recover all of the secrets in the top half here, and you can use the trapdoor tau 2 to recover all the secrets in the bottom half. And so this is why this thing functions as a trapdoor for this ciphertext. And this is already in dual regev form, so it can be used directly in the encrypted CNOT operation. Okay, and so again, the reason that we're able to do this is the reason that this is such a simple trapdoor expansion here is because this only needed to support linear homomorphism. So it can basically just line up the public keys in block diagonal form. So, okay. So that's basically just the main idea. And so what we get is, the final result of this section basically is if you have any classical multi-key FHE scheme that supports nearly linear decryption, you can compile it into a quantum multi-key FHE scheme. And, something that I didn't mention is, most classical multi-key FHE schemes in the literature require a CRS. So, we don't have access to that in our setting. So instead we use the BHP FHE scheme that supports distributed setup. And so it has nearly linear decryption, so it can just be plugged into our compiler. And finally, again, we needed the special ciphertext structure, but this is basically straightforward to achieve with another application of key switching, and then using like the techniques in DOTAS et al. But I'd say the main conclusion here is like it's straightforward. Like if you have a classical multi-key FHE scheme with this nearly linear decryption property, then you can just get right away a quantum multi-key FHE scheme. So yeah, that's going to be. So I have one more part. So if there's any questions, maybe now would be a good time. Cool. Yeah. So finally, I will discuss non-malleable commitments. Right. So let's go back at this point to our template for coin flipping, and let's instantiate it with like the primitives that we've constructed. So now each party is going to sample its random string and use a parallel extractable commitment to commit to it, and then broadcast it, and then everyone's going to prove in parallel zero knowledge that they were consistent in their commitment. So there's one issue to resolve here, and this is a malleability issue. It still comes up. So consider an adversary that's corrupting some party P2, say. In this first stage, there's an honest party P1 that's committing to its string R1, committing to the adversary, right? While at the same time, the adversary is broadcasting its own commitment to its own random string. So it turns out that, what if the adversary could somehow make its commitment to R2 depend on the commitment to R1 being sent by P1? And this is, the fact that the possibility that an adversary could do that is actually not ruled out by the hiding of this commitment scheme. And of course, if the adversary can do that, then it can bias the final outcome R. Okay, so we basically need to solve this issue. And this is solved by using a non-malleable commitment. And so what is the definition of such a thing? Basically, consider any two different messages. Consider this experiment, okay? So now adversaries in this world are called man in the middle. So this is a MIM. And so this man in the middle is interacting with an honest party committing to the message M1 on the left. And at the same time, it's broadcasting its own commitment. And this experiment is going to fix the following distribution, which is the final state of the adversary, as well as the commitment that it broadcasted on the right, okay? And then we can consider the analogous experiment in the case that M2 is being committed on the left. And we want to say that these distributions are indistinguishable. And this intuitively gives non-malleability, right? Because that implies that if M star is distributed indistinguishably in both of these experiments, that means it couldn't have depended in any non-trivial way on which of these messages was sent on the left. Okay, so this is the kind of security we want to achieve. But how would you prove such a thing? If you think about it intuitively, what a reduction will have to do at some point is to interact with the man in the middle. The reduction is going to at some point have to produce this distribution, And so in order to do that, it's going to need to extract from the man in the middle, like what value it committed on the right, while at the same time, not breaking the hiding of the committing on the left, because, realistically, like that's that this hiding is going to be based on some hard computational assumption that the reduction will be reducing to. Okay, so that's kind of the paradigm in non-malleable commitments, is like, how do you extract on the right while maintaining hiding on the left? So, so many works on non-malleable commitments basically just take this tag-based approach, where each commitment comes along with an identity or a tag of the person that committed. Okay, so in the MPC setting, every party is just going to have their own tag. And now the guarantee is that like this non-malleability only holds if the man in the middle's tag, so tag prime, is different than the honest committer's tag on the left. Okay. Now, in order to like build these things, many works just take a two-step approach. So first you show how to construct a non-malleable commitment that supports a very small tag space. For example, like a logarithmic or even less. And then you show some sort of tag amplification theorem. So this I will not touch on at all, because this, in the paper we show such a thing in the post-quantum setting, but it just follows standard techniques. So for this first one, what you could do, okay, so first I will say that, as far as we're aware, there hadn't been any prior works that explicitly studied like, post-quantum non-malleable commitments in the plane model, which is what we want. So we could just take, although what we do note is that like we could instantiate the approach of Pass and We based on complexity leveraging, and in a pretty straightforward way, achieve post-quantum non-malleable commitments under sub-exponential assumptions. Okay, but we kind of took this as a opportunity to really initiate the study of post-quantum non-malleable commitments as well, and so we want to try to reduce the assumption, strength of the assumption as much as possible. So rather than doing that, we'll follow a slightly more sophisticated approach that will give eventually a better assumption. And so this is the approach of Khurana and Sahai from 2017. Okay, so a few remarks about that. So what this approach is it, okay, for small tag space, what a commitment is, it's going to be a mechanism that actually transmits, so it's supposed to be hiding, right? But it will actually transmit the message to the receiver with some small probability. So by small probability, I mean that since it is hiding, this eta has to be some superpolynomial function of lambda. And in fact, this probability is going to kind of be inversely proportional to the actual tag, which we're saying is some integer between 1 and n. Okay. So we want to also set this up in a way where the committer actually can't tell whether the message was transmitted to the receiver or not. And so this is, you can view this as some kind of an eraser channel, and you can set this up using basically statistically sender private 2PC, or a weak version of it that only needs to support indistinguishability-based security. And you can set this up in a post-quantum way using statistically sender private OT from LWE, which was built by Berkeley and Dotling. And this technique of instantiating this erasure channel with OT from LWE was also used in KKS in the setting of witness indistinguishability. So once you have this eraser channel, you can consider the following. If the man in the middle has a tag, is tagged with something that's smaller than the tag of the committer on the left, then this intuitively, it enables this sort of extraction on the right while hiding on the left. Because if this tag prime is smaller, then it's easier to learn the message on the right than it is on the left, just because of how we set up these transmission probabilities. So that's good. So what about the other case? So this is more problematic, but what these works do is basically set up two eraser channels executed sequentially. So one is going to transmit, with 1 over like eta to the tag. The other one is going to be 1 over eta to the n minus tag. So these are executed sequentially, and there's always going to be one of the two that enables extraction on the right while hiding on the left. Okay. And basically, you could show in the proof, you have to use the fact that basically these are like extraction in these two eraser channels is happening with they're independent events, and you can basically take advantage of that to eventually prove security. So this is similar to the approach taken in Khurana and Sahai, and I just wanted to basically finish by just saying a few words about the differences between our work and their work. So they show a reduction. So their reduction is rewinding the man in the middle basically until the commitment on the right is extracted. Okay, so this is no good in the post-quantum setting. So instead we use a non-rewinding proof technique that instead of relying on extraction, we basically can only argue about differences in success probabilities to get the reduction to go through. Okay, so the other thing is that because their goal was reducing round complexity as much as possible, they wanted a 2-round non-malleable commitment, and for that they actually needed complexity leveraging, and which eventually resulted in sub-exponential assumptions. So on the other hand, we're able to leverage in a different way. In particular, we leverage a statistical security parameter. And this gives us the ability to only rely on this very mildly superpolynomial assumption that I stated at the beginning of the talk, which was basically 1 over lambda to the iterated log of lambda. But it's very close to polynomial, but it's an interesting problem. It leaves open an interesting problem of whether you can get post-quantum non-malleable commitments from truly polynomial assumptions. Okay. Now, so I'm almost done. I mean, so now once we have this non-malleable commitment, we can kind of plug it into the beginning of our coin flipping protocol. And it eventually kind of looks like this, where each party commits to their string as well as the randomness at first, and then they send an extractual commitment to their string using this random S. And so this S comes up in the security proof. It's basically another way to tie the non-malleability of this commitment to the extraction of this commitment. And eventually we give basically a proof for this whole thing that doesn't rely on any rewinding and is truly post-quantum. And so basically for details about I won't be able to get into details about the proof subtleties or techniques or anything, but for that I'll encourage you to see the paper. So with that I can conclude. Basically, we have maybe 3 contributions. I mean, so one is a way to extend this recently introduced seemingly very powerful no cloning non-rewinding simulation technique to the parallel or to the multi-party setting. Okay, so we show how to do this, and as we saw, extending it to this multi-party setting has already had applications, as we saw in our paper, but it could reasonably have others. We also give the first quantum multi-key FHE with classical encryption of classical messages, which again may have other applications. And finally, we initiate the study of post-quantum non-malleable commitments. Okay, and then this all is combined to get to our main result of constant round classical NPC, secure against quantum adversaries. And so in terms of applications, there was this paper from last year that they actually constructed a quantum MPC, a protocol for computing any arbitrary quantum circuit. But they had to assume the existence of post-quantum classical MPC. So in particular, our protocol could be plugged into theirs. And we think, maybe there should be more applications, but we leave that to future work. And so that's it. So thanks for listening.
Okay, great. Let me stop the recording.